Okay. So I'm going to repeat so that will show up in the recording. I'm just going to tell you what the empirical rule is. We're not going to get into much details into this one, just to understand what the empirical rule is. It does apply to bell-shaped distributions only. And I will explain it to you, and I'll tell you about those 3% that you see on the handout. So we have a bell-shaped distribution. We have the mean of the ACT score to be 22, and you have a standard deviation to be 3. So what I was telling you on this number line, we're going to scale, the number line, so that will increment by 3 each time. Now, if you go this way to the left, you have to decrease by 3. So that will be, can someone tell me what would that number be right here?
19.
19, and then 16, and then what? 13. That covers almost the entire curve, not all of it. Let me tell you about the tail. The tail, it comes very, very close to the horizontal line, but it doesn't touch it. And this one, now you'll tell me maybe in your graph it touches it, because there is no technology can just show it exactly like that. And this one comes very, very close, keeps coming close forever, but it doesn't touch it. Okay, let me tell you what statisticians from experiments found out when you have a bell-shaped curve. Do you think from 13 to 31 would cover very much of the graph? It looks like it does cover almost very much of the graph, but guys, it's not 100%. It's a 99.7%. So 99.7% of the scores, guys, lie between as low as 13 and as high as 31. So this is the first observation that statisticians made. Now, let me tell you about the 95%. For the 95%, guys, I like you to move 2 standard deviation from the mean. 1, 2, we're here. And 1, 2 from the other side. 95% of the students have ACT scores between 16 and 28. That's a 90. Now you'll tell me, where did they come up with the 95, 99.7%? These are all observations from experiments if the distribution is bell-shaped. Later in the course, we're going to find out that this is really actually true, and we don't need even the experiments. Now let me say one standard deviation within the mean, which is going to be this, guys. This is a big portion of the curve. It's the fat portion right here. Statisticians noticed that 68% of the students have scores between 19 and 25. 19 and 25 is called within 1 standard deviation of the mean. Let me tell you what the word within. If I ask you to come and see me at 3 p.m. and within like 10 minutes of 3 p.m., what do I mean by that? It means you can come 10 minutes early, you can come up to 10 minutes late. That is what it means. And when we say 68% of the data lie within 1 standard deviation of the mean, that means you subtract 1 standard deviation from 22 and add 1 standard deviation 22, so it will be 19 to 25. So here is the summary, guys, and that's what I want you to know here, just a summary of this. 68, if you have a distribution that is bell-shaped, it has to be bell-shaped. 68% of the observation fall within 1 standard deviation of the mean. 95% of the observation fall within 2 standard deviation of the mean. And 99.7% of the observation fall within 3 standard deviation of the mean. Now you'll tell me what happens to the 0.3%. The 0.3% in the case of ACT scores, guys, are the students who score very, very high, like 35, 36, therefore not many of them. And the students who score extremely low, below 13. This is the 0.3%, okay? So this is called the empirical rule. If you come across the empirical rule while doing homework, you just need to know 68% means 1 standard deviation within the mean, 95% 2 standard deviation within the mean, and 99.7% means 3 standard deviations within the mean. Okay. Let me just probably try to answer a couple of questions here on this handout. I just want you to have a knowledge of this. There's not going to be probably one question in the entire chapter 2 about this. What percentage of the scores are between 16 and 28? Can someone tell me? We just went across this one. What would be the answer?
95.
95%, exactly. What percentage of the scores are between 19 and 22? This one, guys. It's within 1 standard deviation of the mean, but from the left, not from the left and from the right. Any guess? It can be 68%, guys. That will be too much because we didn't cover this part right here.
Why can't it be 68 if it falls within 1?
Oh, because it has to be to the right and to the left. I only have it to the left.
Is it 34?
34, it's half of 68, exactly. For the 68, it has to be both this area to the left of the mean and the area to the right of the mean. It's always below and above, below and above. That would be 34%. You see, we can do them without doing any calculations, just knowing the 68, 99, 95, and 99.7%. Okay, I'll do one more and that would be it. What percentage of the scores are between 16 and 25? This one, guys, let me shade it. This one. That's a little bit tricky. Any guesses?
Is it the 99?
No, that wouldn't be 99. That's too much for 99. You still haven't covered this. You haven't covered that, and you haven't covered that. So that's worth something. Okay, let me ask you a question, guys, where I'm placing my, okay. How much is this area right here? This is 2 standard deviation from the left. I got 71.25. We'll see. Okay, let me see what you guys think. Any ideas? Okay, would you guys agree with me if I tell you that this is half of 95%? Agree? No? Yes? This is half of 95 because it's 2 standard deviation to the left. So this is half of 95%. I'm gonna put half of 95 divided by 2. Plus, can someone tell me how much is this? What would that be? This is 1 standard deviation above the mean.
Would it be half of 68?
Half of 68. Here you go. Just add them up, guys. So it will be 47.5% plus 34%. Okay, so that will be 81.5%. However, guys, as long as you understand that 68% of the data usually lie within 1 standard deviation of the mean, 95% of the data lie within 2 standard deviation of the mean, 99.7% of the data lie within 3 standard deviation of the mean. Let me show you a possible question. He will give you the mean. Here's a possible question. Let's say the mean is 20 and he'll give you the standard deviation to be 2. And he'll ask you this question. What percent of the data lie between 18 and 22? Can you guys answer this question for me? What percent of the data, the data is bell-shaped. What percent of the data lie between 18 and 22? Do you guys notice that 18 and 22, to get 18, you have to subtract 2, and to get to 22, you have to add 2. That means it's one standard deviation, so it's 68%. So the empirical rule, to try to memorize this one, 68, 95, and 99.7%. Okay? That is the empirical rule. That's what I want you to know there. And then I'm going to go to the last section, and then we'll have a nice review of chapter 2, which we'll go through the problems together. Okay. This is an easy section, not a difficult one. It's a measures of position. Okay. Let me tell you what the measures of position are. I'm going to use an example to explain this one to you. So I'm going to take this example right here. You have a data set, and we need to figure out the median, first of all, the lowest value and the maximum value. So let's do this one. In order to do that, guys, you have to reorganize the data from smallest to largest. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. What would be the lowest value here? The lowest value, guys, would you agree with me? It's 5.
Yes.
And maximum value?
60.
60. Let's unmute everybody. You guys can unmute yourself when you talk to me anytime. You have the option. All right. Median. I have 15 values, and I need the median. I told you last time, you add 1 to 15, it's 16. Divided by 2, it's 8. So count to the 8th value from any side. 1, 2, 3, 4, 5, 6, 7, 8. That's the median. Okay. Median is right here. Now let me tell you what the first quartile is. A third quartile. First quartile means a quarter, guys. It's the median of the first half of the data set. Well, the first half of the data set is right here. So this is the first half. Can you guys tell me what the median of the first half is? How many values do I have? 1, 2, 3, 4, 5, 6, 7. Would you guys agree with me? It should be 10.
Yeah.
Because it's in the middle. You have 7 values. Add 1 will be 8. Divide by 2, 4. It's count to the 4th one. So first the quartile. Okay, it's called the Q1, guys. That's what they call it in the book. And it is 10 here. First quartile, 1, and Q stands for quartile. Okay, third quartile, guys. Third quartile is the median of the second half. Well, if it was the 4th value in the first half, it has to be the 4th value in the second half, no doubt. So just count. 1, 2, 3, 4. It's right here. So that's a Q3. And that is 30. So you got the median. The median is called the Q2. Q2 means 50%, which I'll explain the percentile. Those 5 numbers are called the 5-number summary. So when you're doing your homework and you are asked to find the 5-number summary, this is what it is. You find the minimum, you find the maximum, you find the median, you find the Q1, and you find the Q3. This is called the 5-number summary. Any questions about how to find this? Okay, let me tell you what a percentile is. If, for example, I tell one of you that you scored in the 80th percentile, what do I mean by that? I mean that you did better than 80% of the students, but it also means that 20% of the students did better than you. That's what a percentile ranking is. So a percentile, guys, is not a grade. It's not a percent. It is a ranking. And it is used a lot in standardized exams. The students receive their scores, they compare their scores, you know, to their peers, and they use a percentile. If I tell you you scored in the 95th percentile, that means you did better than 95% of the students. Like your grade probably is an A, but it doesn't have to be an A, but it's for sure you did better than 95% of the students. The median, guys, is called the 50th percentile because it is right in the middle. So they call it Q2, or they call it P, stands for percentile 50, P50. I think you can guess what the first quartile is. It's called the P25. And the Q3, it's a percentile, is the 3/4 of the data set. It's P of 75. So these are the percentiles and the quartiles. Mainly, I like you to focus on the quartiles, the Q1, Q2, and Q3, because they're part of the 5-number summary. Okay. Let's do another exercise with the 5-number summary. This example right here, guys. Finding the 5-number summary, even number of observation. Here are the travel times to work for 20 New York workers. Okay, the nice thing, I think I put the data in order here, so it's easy. So if I have 20 values, guys, where do you think the median is going to be?
10.
Between 10 and 11, right? Because if you divide 20 by 2, it will be 10, so it will be the 10 between the 10th and 11. So we count 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's between 20 and 25. So what do you guys think is between 20 and 25? You add them up and divide by 2. If you're using StatCrunch is just gonna give you the values. So it will be 22.5. I will demonstrate the calculator as well and show you how to do this. So it's 22.5. First, the quartile, guys. So this is the median. Okay, first quartile is the half of the first half. Middle position of the first half. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the median of the first half has to be between the 5th and the 6th. 1, 2, 3, 4, 5, 6. It's right here. You can check, guys. There are 5 values to the left, 5 values to the right. Okay, halfway between 15 and 15 is 15. That's the first quartile. Third quartile, guys, it's also count 5 between the 5th and the 6th. 1, 2, 3, 4, 5th and 6, between 40 and 45, which is 40 plus 45 divided by 2, which is 42.5. Minimum, what is the minimum value? It's obvious here, it's 5. And the maximum value, guys, is 85. All right, so this is the 5-number summary. It's an important summary. I'm gonna use it in a little bit to check, to show you how to draw a box and whisker plot. And the last thing you remember, guys, when we started chapter 2, we talked about extreme values. They call them outliers. Now we have enough tools to show you how to find if a value in the data set is really an outlier, an extreme value. If you suspect any values in this data set, guys, that could be an outlier, an extreme value, which value would you think it would be? $85. Hamdiya says 85, and I agree. It looks like probably if there are extreme values, but how can you tell? That's how we're gonna find out how to check for outliers. Okay, you're ready? It's very easy process, and I'll show you how to do it, guys. It's right here. Okay. Step 1, you will find a Q3 minus a Q1, which is called interquartile range. So if you are ever asked to find interquartile range, it's a Q3 IQR. In the book, they call it IQR, interquartile range. You already done that. I have already Q3, which is 42.5. And I have a Q1, guys, which is 15. And if you subtract, what do you get? 27.5. That's step one. It's very easy process, but you cannot miss any steps. Step two, you take this interquartile range that you got and multiply by 1.5. Always, it's a fixed number. No matter what the question is, it's 1.5. So 27.5 times 1.5. What is this gonna be? 41.25. Step three, which is the last step before I tell you if we have any outliers or not. So step one, let me repeat. It's a Q3 minus Q1. You get the answer. Whatever answer you get in step one, you multiply by 1.5, you get a new answer. And now look what you do with the new answer that you got. You take a Q1 and subtract the 41.25. And you take a Q3 and you add the 41.25. Okay, what is a Q1 minus 41.25? Q1, guys, is 15. Minus 41.25. That's going to be a negative number, which is what? Negative 36.125. Okay, let's see what Q3 plus 41.25. Q3, guys, is 42.5. And add the 41.25. I got 84. Any guess, guys, how I can tell now if there are outliers using those two numbers? What do you think I'm gonna say, the last statement? Okay, the answer is there is outlier. How did I know that? Based on the last two numbers. Any feedback here? You can put it in the chat if you like. Okay, let's see what we have in the chat. Okay. Oh no, let me tell you how. It's very simple. Once you get those two numbers, any values that falls between those two numbers is not an outlier. Any value that falls outside of the range of those two numbers, then it is an outlier. You know 85 is bigger than 84, then it is an outlier. So if this number, guys, turned out to be 86, then you would have said no outliers because the 85 is below 86. So all values that fall between these two numbers are not outliers, and all values that fall outside of this range are outliers. And this is how you figure it out. So if you have a question to check for outliers, guys, don't try to guess it because it could be a very close call, you know, an outlier or not outlier. Unless if I give you a data set like 1, 1, 1, 2, 3, 7, 8, and then I give you 500 toward the end, it's obvious that 500 is an outlier, but not in here. It wasn't easy to be able to guess. So the steps again, guys, Q3 minus Q1, you find it. Whatever you get, you multiply by 1.5. Then you take Q1 and subtract the answer in step 2. Then you take a Q3 and add the answer from step 2. You get two numbers. All values that fall between the two numbers are not outliers, and all values that fall below the first number and above the second one are outliers.
Can you move the paper down a little bit?
Sure. This way.
Yeah.
Okay. That's how you check for out. And you know, guys, for this one, it was a very close call. 84, 85. So I wouldn't try to guess it, guys, because your guess could be wrong. Sometimes, just, you feel that it doesn't belong there, but it turns out to be one of the values.
Is 85 the outlier? Oh, sorry. Because of the maximum?
No, because it is outside of this range. Any value that's beyond 84, not because the maximum, not necessarily an outlier. Not necessarily an outlier. I'll give you an example where easy to guess that the maximum is not an outlier. Let's say, guys, we have a list of your hourly rates, and all the hourly rates range from $10 to $12, and the last value is 12.25, which is the highest. Well, 12.25 is the maximum value, and probably is not going to be an outlier. So can you guys hear me? Someone told me that they cannot hear me.
I can.
Okay.
But I have a question, like just a real quick one.
Go ahead.
For 15 minus 41.25, I think that's supposed to be negative 26.25, not 36.
Oh, yeah, you're right. It still doesn't, yeah, I agree. Still, all the values that fall between those two ones are all of them except for 85. So 85 is an outlier.
Right.
Yeah, that's for outliers. Okay. Now we're going to show you how to do a box and whisker plot. And you can always use a static range for the box and whisker plot, but I'm going to demonstrate how to do this one by hand, guys. So watch me doing this. And a couple more things in section 2.5 and we'll be done with this. So see how we do the box and whisker plot. Okay. I'm going to do it with this example right here. Okay, you draw the number line. That's a number line. You see what's the minimum and what's the maximum. The minimum is 5 and the maximum is 60. I'm gonna scale this one 10 at the time. I'm not gonna do 5, 6, 7 all the way to 60. So I need to show the 5 and the 60. Look what I'm gonna do, guys. I'm gonna do a 0, a 10, a 20, a 30, a 40, a 50, and a 60. When you use technology, don't worry about that. It will be done for you. But I'm doing it by hand now. All right. Okay. We need the 5-number summary in order to show you how to do a box plot. So I need the lowest value, which is 5. Do you guys agree with me? 5 is halfway between 0 and 10. So you just put a dot right above it, right here in the center. That's the minimum. Then I need Q1, the first quartile, which turned out to be 10. So it's right here. Then I need the median, which is 20, right here, guys. And make sure your dots are aligned horizontally. Then you need the third quartile, which is 30. All right, right here. And then finally, I need the maximum, which is 60. Okay, look what you do now to do the box plot. The first 2 dots, you connect them with the whisker. The last 2, you connect them with the whisker as well. Then here you do this. You draw vertical lines centered. And bingo. That's what we call the box and whisker plot. This, if I look at the box and whisker plot, I know the data is not symmetric, guys. How can I tell that the data is not symmetric? This is not bell-shaped curve. From the box plot, you can tell. How do I know? Any ideas, guys? Why do you think this is not symmetric?
Is it because the whiskers aren't the same size?
Exactly, exactly. So it looks like, you know, it's toward the right. There's a tail toward the right. This is a right skewed distribution. In order for this one to be symmetric, you're correct. You have to have this right almost in the middle, and you have almost to have the same size of the tails or the whiskers. And in this case, you can say that the data is symmetric. So you guys, even from the box plot, you can tell whether you have a symmetric data or not. So that's a good thing to know about box plots. Okay. All right. Here's what we're gonna do here. We're gonna do this exercise together. And now it's to the last part. Practice what you have learned. Use your TI-84. State whether the data in sets A and B represent sample or population. Well, what do you think, guys? Wait times for rides. Is this a sample data or a population data? Do you guys agree this is a data from a sample? Because the wait time, you know, on rides, we have millions of people. So it is a sample data. Most data that you're gonna work with is originated from a sample. To find the range, variance, and standard deviation of each set. Okay, would you guys, I'm gonna pause for a couple minutes and have you work on this one. So what I'd like you to do, for ride A, I'd like you to put the data in L1. For ride B, I'd like you to put the data in L2 and find me the standard deviation. He says the variance and the standard deviation. So I'm gonna pause the recording for a few minutes until, okay. In order to find the standard deviation, guys, you go to Stat, Calc, one variable statistic. My list is in L1, the frequency list. If you don't see the screen, guys, just press Enter. If you see it, make sure your frequency list is empty, nothing there. Calculate. Okay. We're not looking for sigma here. My standard deviation, guys, is S because that's a sample data, not sigma. So my S is 14.5 for the first one. Now let's do it for the second set. See which ride is more consistent. You see what the calculator gives you? It gives you the minimum value, it gives you Q1, it gives you the Q2, it gives you Q3, and the maximum value. It does give you the 5-number summary as well. Now I'm gonna go to Stat, Calc, one variable statistic. Okay. For students who have an older calculator, they're gonna see one var stats on the screen only. You need to type in L2 in order for the calculator to do L2 next time. So, but if you see my screen, you just go to L2, second, and then number 2. How do you get to L2, guys? I demonstrated that last time. You just press the second key and then number 2. Oops. Second, and then number 2. There you go. And now hit calculate. And S is 6.50. So which ride would you guys use if they're both the same rides, pretty much the same rides? Which ride would you use if you were consistent about the wait, if you were concerned about, you know, the wait time?
Ride B.
B, because it has a lower standard deviation. So ride B has a lower standard deviation. It's more consistent as far as wait time. Whereas A, look at the standard deviation. There is another 8 minutes of variation in there. So I would use ride B if consistency is the name of the game here. If not, and you really need to get on ride A, then you would wait, you know, just for ride A. To find the variance, guys, the variance is very easy. Just square 14.5. And to find the variance here, you just square 6.5. This is called the variance. Remember, guys, consistency means, better consistency means lower standard deviation. So for example, on the next test that you take, if I tell you next Tuesday that your standard deviation on the test was 0, do you know what that means? It means that everybody scored the same, just exactly the same, the mean. All of your scores were equal to the mean of the scores. That doesn't have, yeah, well, it does happen sometimes. I'll just give an easy quiz online, everybody gets 100%, yeah, so then the standard deviation will be 0. But let me tell you the other scenario, guys. Let's say your test is out of 100 points, and then I'll report to you on Tuesday that the average score was 75 and the standard deviation was 19. Okay, let me tell you what the 19 is big. It's a big number comparing to 100. It means there are so much variation on your scores. It means some students, a group of students scored very low and another group of students scored very high. That's why we have so much variation in the scores. And then when I ended up doing the average, it turns out to be 75. And that would concern me. Usually I'm not concerned if the standard deviation is low, is small. I get very concerned if the standard deviation is high, because it means there is a group of students who is doing very well, but another group of students is not doing well. And I really need to work, you know, with that group.
I have a question. When you plug in ride A and ride B into the calculator, for L1 and L2, shouldn't they be like separated? Because you put all the numbers at once.
Oh, no, yeah, they should be separated. I made a mistake.
Oh, okay.
Yeah, you're right, 100%.
So I put ride A by itself and L1 and ride B.
Yes, 100%. I agree. Yeah, I made a mistake and then I fixed it, yes. Yeah, let me show you. Now they're both in 2 different sets, if you can see. See, L1 and L2.
Okay, because I had to step away from it. Thank you.
Yeah, that's why, yeah. I didn't look, I wasn't looking at the screen. And oh yeah, with technology, guys, things do happen. You have to be very, very careful. All right. The last part, which is very, very important part. This is a major summary of chapter 2. You need to understand it very well, because this name is gonna be with you until the end of the semester. And you can see what's written here. It's a Z-score. And I'm gonna explain what a Z-score to you is. Let me see. Oh, the range of each data set. We didn't answer this question. The range is you pick the lowest value and the largest value. So the range of A, let me just answer this one. The lowest value, I think it's 11. And the largest is, I believe, 60. 60 minus 11, which is 49. And let's see the range of B. The range of B, guys, the largest number, I believe, is 50. And the smallest is 31. Yeah, you see, it's even smaller range here, 19. So the range of B is 19, range of A is 49. Okay. Z-scores. Let me explain this to you and show you what a Z-score is. And once I finish, you just use a formula to find a Z-score. Let's say you have a data set that has a mean equals 50, and it has a standard deviation equal to 10. So I'm gonna scale this line with the standard deviation. So I'm gonna add a 10 here, a 10, a 10, then a 10 from this side. So can you guys help me? This will become 60, 70, and 80. This will become 40, 30, and 20. Okay. I'm gonna ask you a few questions here. Let's say the average score, let's say this is a test score. It was 50 and the standard deviation is 10. Someone scores 60. If I ask you how high above the mean this person scored, what would you tell me? What's the difference between 60 and 50?
10.
10. So you guys agree with me that this person scored 10 points above the mean, correct? Okay.
Yep.
10 points is how many standard deviation? What's the standard deviation? It's 10. So I can say that this person is 1 standard deviation above the mean. Then a person will come to me and tell me, well, what do you mean by this one standard deviation? I'll tell you, the standard deviation is 10. So you're 10 points above the mean. So yeah, that does make sense. What would you say about that person the students who scored 40 here?
There was deviation below the mean.
1 standard deviation below the mean, because this person is 10 points below the mean. The mean is 50. So that's 1 standard deviation below. What about this guy right here? 20. What's the difference between 20 and 50, guys? 30. That's 30 points below the mean. How many standard deviation would that be?
3.
3 standard deviation, guys, because it's each standard deviation is worth 10 points. 10, 10, 10. That's. What about the guy 80 here who scored 80? This guy has 30 points above the mean. Each 10 points is worth 1 standard deviation. So that will be 3 standard deviation above the mean. When it comes to test scores, guys, would you want me to make a statement to you that you are standard deviation above the mean or below the mean? Which one would sound better to you?
Above.
Above the mean, definitely. The more standard deviation you guys are above the mean, the higher your score is. So you wanna be on this side, not this side. This is the positive side of the standard deviation, guys, and this is the negative side. Now, instead of saying this person is 1 standard deviation above the mean, I can say the Z-score is 1. So the Z-score, guys, is to tell us how many standard deviation does a value deviate from the mean. That is what the Z-score. So I'm gonna write it down. How many standard deviations a value deviates from the mean. That's what we call a Z-score. Okay, we're gonna do it for 60. Okay, let me show you how to find it for the value 60, guys, and then okay, how did we figure out? We say 60 is 10 points away from the mean, so we said it's 1 standard deviation above the mean. But look what you can do. The Z-score is labeled by Z. You take the X value, which is 60. You subtract the mean. I'm gonna write the formula in a second. What is the mean, guys? It's 50, and divide by the standard deviation, which is 10. 60 minus 50 is 10, divided by 10 gives you 1. That is the Z-score. The Z-score is 1 here. Let's take a value 40, guys. What do you guys think that the z-score is going to be here before I calculate this one? This is one standard deviation below the mean. Would you agree with me that it's going to turn out to be -1? Watch. You put the value first, which is 40 minus 50 divided by 10, which is -10 divided by 10, which is -1. That is called the z-score. Now let me pick a different value. It doesn't have to be any of those values. Now, since I know the formula, let's say a student scored 68. And I want to figure out, what the z-score is. So you take the 68, you subtract the mean, and divide by the standard deviation. 68 minus 50, guys, is 18, divided by 10, which is 1.8. And the formula is, guys, this is the formula. I'm going to write it down here. Z equals z-score equals value minus mean divided by standard deviation. Or you can write it like this: x minus the mean divided by sigma. That is the z-score. I have a colleague of mine on his syllabus. He explains the grade of students based on z-scores, and I'll give you some more examples in a second. Or it could be this formula. I want the students probably to tell me what's the difference between those two formulas. They lead to the same thing. X, the value, minus the sample mean divided by the sample standard deviation. Here, the value minus the population mean divided by the standard deviation. Those two formulas are the same. If you have a population, this is how we label the formula. If we have a sample, this is how we label it. But at the very end, guys, you do the value minus the mean divided by the standard deviation. So if I tell a student, I want to use a coding language next week. I don't want to tell the students the exact score, but I send a text to a student and I tell him or her that your z-score was 2.2. Should the students be happy? What do you think at a z-score of 2.2 on the test? Is this a good thing or not a good thing? Any comments? Okay, students who say not good, why?
Don't we have to know the mean first?
Well, no, it's not about knowing. It's whether the students should feel that she's done very good when I tell her that your z-score is 2.2. We don't know what the score. Yeah, I need to know the mean and the standard deviation in order to find the actual score. But if I tell you that your z-score is 2.2, guys, you should be very excited. That means your score is 2.2 standard deviations above the mean. Remember, guys, we cannot go beyond the 3 standard deviations. Once we go beyond the 3 standard deviations, you're above the 100% because 99.7% covered within 3 standard deviation. So a z-score of 2.2, guys, it means you're beyond the 95% because 2 scores is 95%. One standard deviation is 68 and 3 standard deviation 99.7. A z-score of 2.2 is very good. That means you're above average. What about if I tell the students your z-score is 0? What does that mean? It doesn't mean that the students score a 0 on the test. No. Anyone can tell me what the z-score of 0 means.
You got the average score.
You got the average score. Exactly. You are right at the average. But should you be concerned if I tell you your z-score is -1.8?
Yes.
Yes.
You should be very concerned, guys, because that means that your score is below the mean. It is 1.8 standard deviation below the mean. Your score is below the mean. Now, it won't happen that I tell the students that your z-score is 3 or 4 or 5. This is not gonna happen. A z-score actually can go beyond the 3 standard deviation. If it goes beyond that, we say it's very unusual. It's an outlier. So I'm going to give you a summary of how high the Z-scores can be. They do not usually exceed 3, you know, just in a good data set. So if I tell you guys your Z-score is 3, you can be assured that your score is probably the highest, you know, just in the class. But if I tell you your Z-score is -3, probably the students should consider dropping the class because it's way, way below the mean. It's a 3 standard deviation below the mean. I hope no Z-scores will be that low. But will there be always a negative and positive Z-scores in my class? Definitely. There are some, let's say the average is 80% and a student scores 79%. This student's Z-score is going to be in the negative because it's below the average. And if a student scores above 80%, the Z-score is going to be in the positive. So a data value is usual if the Z-score, guys, is between -2 and 2. If you get a Z-score between -2 and 2, this is a usual value. We'll deal with it. But a data value is unusual. I'm just going to put the unusual here. If it is more than 2 or less than -2. So examples, guys. Z equals 2.7. That's unusual. Here, example, Z is 1.7. That is usual. Anything that falls between -2 and 2, guys, is usual. Anything that is bigger than 2 or less than -2, it's unusual. Let me tell you what very unusual is. It's very unusual if Z is bigger than 3 or Z is less than -3. That will give you very unusual data sets, data values. Okay. So that is what the Z-score is. The last question we're going to do together is to use Z-scores in applications. We're going to do this application together and we'll wrap it up. So it's example 2. SAT vice ACT. Eleanor scores 680 on the SAT, and the distribution of SAT scores is symmetric and single peak. That means it's bell-shaped with the mean of 500 and a standard deviation of 100. Gerald takes the American College Testing ACT math test and scores 27. ACT scores are also symmetric with single peak distribution, but with the mean of 18 and a standard deviation of 6. Find the standard Z-score of each person and tell which one did better relative, you know, just to comparing, you know, to the other. So we're going to do this. Find the Z-scores. Okay, I'm going to start with the SAT, guys. We know the mean is 500 and the standard deviation is 100. And what's the Z-score for Eleanor? Okay, how do you do it? The formula, the X value, how much, what did the Eleanor score? 680 minus 500 divided by 100, which is 1.8. Okay, now let's do the ACT, which is Gerald now. What was the mean for the ACT score? They say the mean is 18 and the standard deviation is 6. What was the Z-score for Gerald? So Z equals. So this is for Eleanor's, I'm gonna label it as E, and this is for Gerald, which is G. The X value, guys. What did he score? 27 minus 18 divided by 6, which is 1.5. So who has the higher score, guys? Is it Eleanor or Gerald?
Eleanor.
Eleanor, the higher the Z-score, the better your performance comparing, you know, to the rest of the class. You wouldn't be able to tell, guys, by not doing the Z-score, because we have two different situations, two different grading criteria, SAT and ACT. You cannot just compare apples with oranges. But when you do Z-scores, yes, you can compare. The one who has the higher Z-score perform better. So, Eleanor has the higher score because her Z-score was higher. So this is for Z-scores, guys. It's very, very important to understand that. We'll be using them a lot, so I want you to practice it quite a bit. This is the formula. The Z-score is the actual value minus the mean divided by the standard deviation. When you convert values to Z-scores, you can compare them, because prior to that, you can't, because they're two different things, SAT and ACT. But once you compare to Z-scores, you change to Z-scores, you can compare values. So that concludes everything that you need to know in this chapter. And let me tell you what I'm gonna do. If you guys show up for office hours today, I'd be willing, you know, just to go over the review exercises. But in the meantime, if you don't, we're not mandating the office hours on you guys, but they supplement, you know, just the teaching. So try to do the chapter 2 review exercises. I will review them tomorrow before I start chapter 3. You have quite a bit of exercises here. This is one. Standard deviation, 5-number summary that we just did today. Outliers. So if you guys can work on them, you know, just between now and the time I hold my office hours, and then if you have any questions, we can go over those questions. This is another one, a box and whisker plot, a box plot. It's important, that's why I have quite a bit of box plots, but I'll go over some of them tomorrow with you. Okay, so that will end the discussion of chapter 2. We will begin chapter 3, and guys, please remember, you have quite a bit of work this week. You're gonna complete chapter 2 and 3, and you're gonna take the test on Monday. If you have any questions, feel free to ask. If not, I will see you hopefully this afternoon if you can make it, and if not, I'll see you tomorrow morning. Make sure to key in your name so I can keep track of attendance, please. Yes, I'll send the scan since we finished this one. Thank you, guys.